Yes, sir.
Okay, thank you. So in the previous class, we have gone through the operation of depletion type MOSFETs. So in this lecture, we will be proceeding with the operation of enhancement type MOSFETs. So for basic understanding, we will be just analyzing the N type MOSFET, and the similar analysis will be for the P type also. So we will consider here the N type or N channel enhancement type MOSFET. So in construction wise, we have already seen there will be a substrate. On that, we will be having two different N regions. If it is N channel uh, enhancement type MOSFET is there, two different N regions we will be depositing. So this will be with respect to the diffusion, like two different regions will be diffused. So this is N plus doping will be there. So doping will be higher, quite higher, like N plus doping will be there. And this substrate is of P type. And here this is oxide and this one is metal. Okay. And this metal will connect into gate terminal. So it is metal oxide and semiconductor connection is there. Here there is no channel. Initially there is in this region there is no channel. Okay. So this is the enhancement type MOSFET. Initially there is no predefined channel is there. So construction wise, this is the structure. This is drain terminal, this is the source terminal, and this is gate terminal. Okay. So the next to start with the operation, we will just consider like, so what is the difference basically? So in terms of depletion and enhancement type MOSFETs, the difference is there is no channel in enhancement. Okay. So we need to create a channel to have some conduction between drain and source. So to create a channel, we need to apply gate voltage that will be such that it should be attracting the electrons in this region, channel region. So this is the channel region. These two source and drain of N type. So the channel should be such that it should be having electrons available into this region, channel region. So this is our channel region. So here we need to attract electrons so that the this drain and n type source are there. So there will be a direct path between source and drain with the help of channel. This channel will be having majority electrons. So for that we need to apply gate voltage that should be either 0 or greater than 0. That means gate voltage should be greater than or equal to 0. We need to bias the gate voltage. So with respect to that, channel will be formed, and now we will be able to conduct the current based on the drain to source voltage. Okay. So we will just see. So in enhancement MOSFET, no pre-existing channel is there. Here the channel will be induced. Channel is induced by applying gate to source voltage. We need to induce the channel by applying gate to source voltage. And also in difference to the depletion type MOSFET, in enhancement type MOSFET, so these enhancement type MOSFETs are considered to be modern MOSFETs than the depletion type. So they are like modern MOSFETs, and in that instead of using metals, we will be using Yes, am I audible?
Yes, sir.
Uh, Someone is able to join Mukala. What is his name? I've got a notification, that's why. Okay. So we were talking about the enhancer type MOSFET. So here it is a MOSFET. There, instead of using metals, what we do, we use in modern MOSFETs, we use polysilicon. So it will be using by replacing the metals. So there are some advantages associated with this use of polysilicon. So we will see like it basically used, if polysilicon is being used, the overall size of the device will be reducing. Okay, so it reduces the device size if we are going to use polysilicon instead of metal. And also polysilicon is less costly than the metals that we are going to use, so it is less costly. And also it helps in like if we are using polysilicon, the fabrication process is simpler than the using another metal, like we are going to use like aluminum. So polysilicon provides better fabrication process, simplified fabrication process. So we can write simplified fabrication process. So there are different advantages associated with using polysilicon if we are going to use. So metals can also be used, but in modern like MOSFETs, these metals are replaced by polysilicon. So basically we are going to use the metals only. So while going to analyze the operation, basically we will be applying different voltages. So one voltage is gate to source voltage, another one is drain to source voltage. Okay, so by applying these two voltages, we need to analyze the device, like how it is going to perform. So first, suppose we are going to apply VGS, that is greater than or equals to 0, and at that time VDS, suppose we are going to apply is 0. If this is the case, that means here at the gate side we are going to apply some positive value. Okay, but this drain is like connected to ground, or you can make it like it is not connected to anywhere, like it is open, or just we can call it like it is connected to 0. Okay, so if this is the case, at that time what internal processes will be happening is here. So as we are going to apply the gate voltage that is positive, so as we are going to apply positive gate voltage, there will be because of this positive gate applied voltage, so whatever the minority charge carriers are available into this p type, that is electrons, so electrons will start accumulating near the oxide layer. Okay, as we are going to increase the gate to source voltage further in positive direction, it will keep on increasing the electrons accumulation near this SiO2 layer. So by accumulating the electrons near this oxide layer with the help of increasing gate to source voltage, this is VGS. So we are going to increase VGS such that the electrons are accumulating near this. So this accumulation of electrons near this SiO2 layer will form our channel. This will form form channel. Okay, so you can just here write like in enhancement type MOSFET, channel is formed by applying positive gate to source voltage. Okay, so as we are going to apply positive gate to source voltage, the electrons will be attracted near electrons, that is minority carrier in p-type substrate will be attracted towards the SiO2 layer or oxide layer. Towards oxide layer, the electrons will be attracted, and this attraction will be because of the electric field produced because of the application of gate to source voltage. Right, because of the electric field produced by applying VGS. So as we are going to apply VGS, there will be an electric field near this oxide region. So this electric field will be attracting the electrons available into this p-type substrate. So this accumulation of electrons will be taking place, and this accumulation will be such that it will be forming a channel. So this is how the channel is induced. So this channel that is formed is called induced channel. Okay, and also at that time, as drain voltage, a drain terminal is connected to zero, or it is connected to ground, like it is not having a positive voltage connected. So whatever the electrons have been generated, that electrons will be available here only. There will be no conduction of electron taking place between source to drain, or there will be no electrons moving from source side to drain side because drain side is connected to zero. So at that time, the current through this will be zero. The current flowing in that case will be a zero. You can just write, so ID will be zero if no drain voltage is applied. Even if the channel is formed, but if we are not applying any drain to source voltage, or drain voltage is connected to zero, there will be no current flowing. So at that time, the channel that is formed when there is no current is flowing because of no application of drain to source voltage, this channel is called flat channel. So that here the channel will be flat. So here channel is flat. So this induced channel is basically flat when there is no drain to source voltage. So this was the case when VGS we are applying, that is either 0 or greater than 0. So we are able to track the electrons, minority carrier electrons that is available into beta substrate, and it is going to form the channel. So this is an induced channel, and there is no current, as we have made drain to source voltage 0 or drain terminal to 0. So now the current will only be flowing if we are going to apply the drain to source voltage. So if we are going to apply the drain to source voltage, that means here the another case is like we have made VGS is equals to some fixed value that is sufficient to form the channel, and then we are going to apply VDS. So now second case, like So this is the first case, you can call it. And in second part, we are going to make the VGS fixed. That means we have made VGS fixed means we are able to form the channel. So once the channel is formed, now we are applying the VDS. So VDS will be applied. So VDS will be applied such that VDS will be positive. Okay, we will be connecting the VDS to a positive voltage. So in that case, now what will basically happen is we will see that. So now as the channel is formed, electrons are available here. Okay, so as electrons are available here, we are going to apply drain terminal with the positive voltage. So this positive voltage will be attracting these electrons available into this channel region because of application of gate to source voltage. So these electrons will be attracted. So electrons movement will be taking place by this arrow. Okay, so opposite to this arrow or electron movement, the current direction is there. So the current direction will be this way. Okay, so the current direction will be in this way. This is the direction of current, that is called ID, drain current, and the electron direction will be from here to here. That means from source to drain. So source to drain, electron direction will be there from source to drain. So opposite to source to drain or electron direction, current direction will be there. Okay, so this movement of electron will be taking place as we are going to apply drain to source voltage, that is positive. Okay, so here induced channel is there, available with plenty of electrons available for conduction. Okay, so now we are going to apply VDS is, you can write like positive VDS is applied. Positive VDS is applied. So VDS will attract, basically the positive VDS will attract, we can write positive VDS is applied and attracts electrons available in channel region. So whatever electrons are available into the channel region, it will be attracting the electrons, and this movement of electron basically constitute the drain current. Okay, so ID will be because of this movement of electrons available into this channel region, and that movement will be because of the applied drain to source voltage. Okay, so this is the basic idea, like how the current is going to flow and how the channel is formed. Okay, so once we have seen this, now this is the case when we are applying the VDS, but this VDS is small. We have applied the VDS, but with this VDS is small, then this type of uh, phenomena will be taking place. And there also, as we are going to apply the VDS, we can just see. So between this is an N type and this substrate is of P type. So this is N and P. So this is NP, or that is there is a diode available because of this N region and P region. So this is a diode available is there, and as we are going to increase the VDS, drain to source voltage, so drain to source voltage, whatever positive drain voltage we are applying, with respect that the source, or sorry, this substrate is connected to ground, we can call it the source, the substrate is connected to ground. So this N is connected to positive side and P is connected to 0. So this is like a reverse bias PN junction. So as we are going to increase this drain to source voltage, there will be an increase in reverse bias to this uh, PN junction diode. So as the PN junction diode is going to increase this uh, uh, reverse bias operation, there will be an increase in depletion region. So this black region, that is shaded region, is showing the depletion region. So this is the depletion region taking place as we are going to apply the drain to source voltage. So but this depletion region will be more near this drain side than this source side. Why? Why there will be more depletion region near this? Because if we compare these two diodes, so this is N and P, so there is one diode here, so we can just see. So this is P side and this is N side. Okay, so we can make it like there will be one diode here. This is P and this is N. Another diode is here. Okay, between this is P and N. So we can make it like this. So one diode is here. So there are two different diodes, and this is also a reverse bias because this is having positive side drains and this is ground. But this one is like this is connected to again ground, this side, this terminal, and this substrate terminal is also connected to ground. So it is like both the directions are having the same potential. That means this is having the ground connected to ground and this is also connected to ground. But in this case, this is connected to positive and this is connected to ground. So that means this diode that is on drain side is having more reverse bias than the diode that is on source side. So that's why there will be more depletion region near this drain side. So because of this, there will be more depletion region. So this depletion region has increased on the drain side, but on the source side, it is having similar nature. Okay, so there is less depletion region, but on the drain side, there is more depletion region. So because of this depletion region, there will be reduction in channel region. So initially the channel was flat. Okay, so initially the channel was like flat. It was a flat channel. But because of the application of drain to source voltage, as we are going to increase the drain to source voltage, there will be the case like the channel is going to tapered. That means initially it was flat, now it is being tapered. That means this tapering is going to take place because of the reverse bias uh, this PN junction diode on the drain side. And as we are going to increase this drain to source voltage further, there will be further increase in depletion region, and there will be the case like the channel will reduce further and it will break from here. So the point from which the channel is going to break or channel is going to reduce is called the pinch off point. Okay, so as the channel is going to break, the start or the beginning of breaking of the channel is going to call the pinch off point. So that analysis we will just do by applying the uh, drain to source voltage. So in this point we can write there will be depletion region near drain and source side, or we can call it like the depletion region will be like similar. There will be similar depletion region, a region near drain and source sides. So both sides the similar depletion region will be there if we are going to apply the drain to source voltage that is small. Okay, so now we will see the third case like if we are going to apply VGS that is fixed, and this fixed value is such that channel is that is fixed value is sufficient to make the channel is formed. Okay, So this VGS is fixed and that is sufficient to make the channel. And now we are going to apply the VDS, and this is larger value. Okay, so we are applying the VDS, that is positive voltage, and here also the VDS that we are applying is positive voltage, but it is small. Here we are going to apply the positive voltage, but it is large value. So as it is large value, the current with respect to that, as we are going to increase the uh, drain to source voltage, the current between the source and drain will be increasing, keep on increasing till the channel is going to pinch off. Okay, so current will be increasing. At that time the gate to source voltage is fixed, so gate to source voltage is fixed, and VDS we are increasing, so current will keep on increasing till the point reach called pinch off. So at pinch off the channel is going to deplete, the channel is going to break. Okay, so this is the point from which the current flowing between drain to source side will be a constant, it will not be increasing further as we are going to increase the VDS. Okay, so here also in this way, here we can write one more term, the drain current will increase, so ID increases as VDS increases. So as we are going to increase VDS, the ID will be increasing if we have applied the VDS small. So in this case, now as we are applying the VDS that is large, there will be larger depletion region near the drain side than source side. Okay, so larger depletion region will be there near the drain side than the source side. Because of this larger depletion region near the drain side, there will be tapering of channel occurs near drain side. Okay, channel tapering will be taking place. The voltage VDS applied for which the channel starts depleting, or you can say channel starts breaking from drain side is called pinch off voltage. So whatever drain to source voltage we are further going to increase, because we are increasing the drain to source voltage further. So there will be a time when the channel has tapered and now it starts depleting. Okay, so it starts depleting means we can, in the symbol form we can just see, like if this is the case, the instead of channel here it is up looking like here, so instead of there the channel will further deplete and it will be extended up to here only. So now this will be the channel. So for this portion, so for this region the depleted channel is there, or there is no channel. In this region there is no channel. Okay, so now that means the channel is going to deplete from this portion, from the drain side. So this is going to deplete the channel. So as we are going to increase the VDS, so the point at which the depletion starts is called the pinch off point. So that VDS at which the channel starts depleting is called the pinch off voltage. Okay, and beyond pinch off current, that is ID, becomes constant, or we call it like the current is saturated. Okay, so this is called saturation current. Now the drain current will be saturated, so this is called saturation current. And the VDS value at which the pinch off occurs is called VDS, VD saturation, called VD sat. It is called VD sat. And just write like VD sat. So VD sat is the value of VDS, that is drain to source current, drain to source voltage at which the pinch off is going to occur, and beyond that there will be a constant current, that is saturation current, will be flowing through this source to drain side. Okay, so by going with the analysis we can just see the transfer characteristics and the drain characteristics. So transfer characteristics will be ID and input voltage, that is VGS. So ID versus VGS will be showing the similar curve, that is of the normal diode. So for the normal diode, as we are going to increase the diode voltage, it initially there will be a zero current, and at a point there will be increase in the current. The point at which the increase in current will be there, that is called VT. This is called threshold voltage. This is called threshold voltage. So this threshold voltage is the voltage at which the channel has been formed, and at that time the drain to source voltage is also applied and the current starts flowing. So here initially we have seen like drain terminal we have connected to zero, and we are applying the gate to source voltage. So gate to source voltage we are applying, but drain terminal is connected to zero, there will be no current flowing, but there is a channel formation is there. So when the drain to source voltage is also applied, and we are starting to apply the gate to source voltage, so the point or the gate to source voltage at which the current starts flowing is called the drain threshold voltage. So we can just analyze like in terms of symbol, if we call it like, if this is the just a minute, okay. So this is the symbol of we can call it, this is the symbol of n channel drain. Okay, so here this is gate and this is drain and this is source. So we are going to apply, suppose we have applied the drain to source voltage that is positive, and at that time we are increasing the gate to source voltage. Okay, so this is n channel enhancement type MOSFET. So as we are going to increase, at that time there is a drain to source voltage connected. So as we are going to increase the gate to source voltage, so this plot is for constant VDS, for constant VDS this plot is there. So if suppose the VDS that we are connecting is a constant VDS, so some VDS is there, and now we are going to increase the gate to source voltage. So as we are going to increase the gate to source voltage, there will be accumulation of electrons will be taking place up to this voltages, gate to source voltage that we are applying. So in this region This is the gate to source voltage region, gate to source voltage, where the electron is accumulating near SiO2 or oxide layer. Okay, so as the electrons are accumulating, if the sufficient amount of electrons are sufficient, channel has been formed, then only the current will be starting. Okay, so this as we are going to increase the VGS from 0 to some value, and at this value there will be channel is formed, and now the current will start flowing. So this value of VGS at which the channel is formed and current starts flowing is called the threshold voltage. So the minimum, that means minimum threshold voltage value we need to apply this gate to source voltage. So gate to source voltage should be applied up to a minimum value, that is VTH, that is threshold voltage, so that there will be a current flowing through the MOSFET. So this is your threshold voltage. Okay. And next one is drain characteristics or output characteristics. Okay, so in output characteristics, ID versus VDS, that is output voltage. VDS and ID will be plotted. So as we are going to plot, so this is plotted for a constant gate to source voltage. So suppose gate to source voltage is plus 8 volt. So gate to source voltage we have applied, that is sufficient to form the channel. So channel is formed. Now we are going to increase the VDS. So as we are going to increase the VDS, and consider this one. So as we are going to increase the VDS, the current is increasing linearly. So this is called linear increase in current. So as the linear current is increasing, after a point the current will be constant. So the point at which the current will be constant is called the pinch off voltage. So this will be the point at which the current is being constant. So this is called pinch off voltage. Okay, so for this case this will be your pinch off voltage. So this pinch off voltage is also called VD set, and this VD set is equals to VGS minus VT. So this VD set is equals to VGS minus VT. That means we need to apply extra uh, gate to source voltage minus threshold voltage. So whatever the remaining voltage is there, that much drain to source voltage we need to apply so that the current is becoming constant. So this is called VD set, and the region of operation where it is operating in linear mode. Okay, so this is going to operate in linear mode. Okay, so up to here it is linear mode. So this is called the linear region operation. So this is called the linear region of operation of the MOSFET, or it is also called triode region. So the region where the MOSFET is going to operate in linear mode, that means the current is going to increase with respect to increasing VDS, is called the linear mode. And the point after pinch off, this is the point of pinch off, are called saturation. So this is pinch off point. Okay, so this pinch off point, after pinch off point the current is going to constant. So in all the cases the current is going to constant. So this is called your saturation region. Okay, and the region where we are applying the gate to source voltage, but even in that case also the current is going to be zero. That means whatever drain to source voltage we are applying, the current is zero. That means the region when gate to source voltage is less than, so the gate to source voltage is less than the threshold voltage, that region will be called the cutoff region. Okay, so the cutoff will be when, so cutoff is when VGS is less than VT. If VGS is less than VT, that will be your cutoff region. So in cutoff region, there will be zero current flowing through this drain terminal. So this region up to here, by this we can call it, this is cutoff region. Cutoff region means if we are applying gate to source voltage that is less than the threshold voltage, then there will be no current flowing. So this is called cutoff region. Okay. So this is your drain characteristics and transfer characteristics. By combining these two, we can just see the transfer characteristics can be plotted from the drain characteristics also. So if drain characteristics is given, then also we can plot the transfer characteristics. So this is like we can extend it. So for different voltages, so this is like 3 volt VGS. So at VGS 3 volt, whatever the current is flowing, this is the current. So at 4 volt, what is the current? At 5 volt, we will be plotting different points. So at 6 volt, this is the current value, and 7 volt, this is the current, and at 8 volt, this is the current. So by combining these points, we can get the transfer characteristics in case of N type MOSFET. Okay, so I hope you have got the point. So is that clear to everyone? Okay, so have we got the points like whatever I was trying to say? So this is a basic of operation of normal and channel enhancement type MOSFET. The similar analysis we can do for the P channel MOSFET also, but the only difference will be there, like instead of using positive gate to source voltage, we need to apply a negative gate to source voltage. Okay, and that case, once we are going to apply the negative gate to source voltage, the instead of attracting the electrons, it will be attracting the holes from this p type substrate, sorry, n type substrate. So it is a n p channel for p channel MOSFET, p type MOSFET, we need to have n type of substrate. So n type of substrate, so minority holes will be attracted towards this by applying the gate to source voltage, that is negative. And also this is p, instead of n there will be p channel regions, highly doped p channel regions for drain and source. So here, to attract the holes from this p, we need to connect negative voltage. So here drain to source voltage should be negative, okay, to attract the holes from the drain side. So this is the basic operation of uh, N channel MOSFET. So now we will go with the current equation. So different current equations are given. Current equations we will be proceeding. So there are basically 3 different regions where this MOSFET is going to operate. So one is cutoff region. So MOSFET and MOSFET, that is enhancement type MOSFET, will be operated in cutoff region. So the condition for cutoff region is like the current flowing will be 0 in cutoff region, and the condition will be when VGS that we are applying is less than VT. So if VGS is less than VT, the current flowing will be 0, and this is called cutoff region. Second case is linear, or we call it triode region. So the condition for triode region is we need to apply the VGS that is greater than VT, that is threshold voltage. Now that means the channel has been formed, and as the channel has been formed, okay, so this is the linear region. So we need to have the channel formed, and this was the point. Okay, so one more point, like we have seen, this is the point VD set. So the VD set for different gate to source voltage is different. So if we plot all the VD set points, we will be getting this dashed line. This is called locus of VD set. Okay, so all the locus of VD set will be like a curve. So this locus of VD set is given by this curve only. Okay, and all this VD set will be different for different gate to source voltage, because VD set is equals to VGS minus VT. So VT will be fixed, but VGS is reducing. We are reducing the VGS. So as we are reducing the VGS, the VD set value will also be reducing. So initially it was here, now it will be less than. For this it is further less. Okay, so you can have it. Okay, so for this, so we okay, so VD set value is going to reduce. So if we plot this, this is the region where it is operating in triode or linear region. That means this is the VD set. So up to this, the VD value that we need to have. So this VD value, VDS, should be less than VD set. Then only it will be operating in linear region. Are you waiting from this? So for linear region, the VDS that we are applying should be less than the VD set, because this is the VD set for this condition. VGS is equal to 8 volt, and this is the point for VGS is equal to 7 volt. So if we are applying VDS less than this VD set up to this region, from here to here, from here to here, this is the region of linear region operation. Okay, so the condition for linear region is, first condition is we should be having VGS greater than 0, and along with that we need to have the condition like VDS should be less than VD set, or VDS should be less than VD set is given by VGS minus VT. Okay, so this will be the condition for the case like the MOSFET is operating in linear region. So if it is operating in linear region, there will be a current flowing, and that current will be given by the equation like the ID. In that case, ID in that case is called ID linear, because it is the current in linear region. So this is ID in the linear region. So that linear region current is given by mu n cox W by L VGS minus VT into VDS minus VDS whole square. Okay, so this is the current equation in case of linear region. So here, as the MOSFET is going to operate in linear region, the current will be given by this expression. So this mu n here is the mobility. Mobility of, if it is n channel MOSFET, there will be mu n. If it is p channel MOSFET, it will be mu p. Mobility of hole and mobility of electron. Okay. So mu n cox W by L VGS minus VTH into VDS minus VDS square by 2. This is the current equation in the linear region. The next we will see, that is saturation region. So in saturation region, first of all, what we will see is what is the condition. So the condition is VGS should be greater than VT. So first condition is such that the channel has been formed and there is a current conduction taking place, and VGS is greater than VT, that is giving you out like the transistor is on. Okay, so if transistor is on, along with that, in the saturation, you can just see from here. So the region of saturation is, this is the region of saturation from here, from this point to this point. Okay, so from this point to this, so from this point to this is your saturation region up to here. Okay, so this is your saturation. So saturation starts with, like, if we are applying VDS greater than VD set, this is the point of VD set. As we are going to increase the VD set voltage, the VDS greater than VD set. So this is the VD set. If we are increasing the VDS greater than VD set, then the saturation starts. Okay, so saturation starts with the condition like the VDS should be greater than VD set, or VDS should be greater than VGS minus VT. So this is called the saturation region. So in saturation region, the current equation is given by ID, that is ID saturation, is equals to mu n cox value. What is there, I will be explaining. Okay, so we will get that point. Cox W by L VGS minus VT to the power 2, and also it is 1 by 2 is there. Okay, and just consider it is 1 by 2 times this. So from where it has came, so this equation, so by putting the VDS, by putting VDS is equals to VGS minus VT in the linear one, we will be getting this expression. So if we are going to put from here to here, we can just see in this equation, if we are going to put VDS is equals to VGS minus VT, then we can get the expression for saturation. So why we are putting? Because beyond this VD set point, whatever VD set value will be there, that will always be VGS minus VT only. In practical simulation we do for the circuit, even if we are increasing the VD set, the VDS value, VD set value will always be constant, like VDS will always be the same VD set only. So beyond this pinch off point, whatever VDS value is there, that is always VGS minus VT only. Okay, so that's why it is by putting this we can get this expression of the saturation current. Okay, so I hope you have got this point. So this is all about the working of n-channel MOSFET, n-channel enhancement type MOSFET. Okay, and if you have any doubt, you can ask, and you can just write here also. Mu n is here, mobility of electron. W is width of channel. L is length of channel, and COX. COX is called oxide capacitance. So COX is also given by, so oxide capacitance is given by this is called uh, permittivity, like epsilon oxide, whatever the permittivity of the oxide layer is there, as a SiO2 is there. So in that case, that will be there, and TOX is the thickness of the oxide. So in this graph, you can just see they started. Okay, so suppose this is the SiO2, and this is called the thickness of oxide. This is oxide. This is the permittivity of oxide, that is represented by epsilon ox. Okay, and this is going to have give you the length. This is the length of the channel, and this is called the width of channel. Okay, so in this is like a 2D structure is there. So in 3D you will be able to clearly identify what is width here. So width is basically once we go with the 3D structure. Okay, so for the basic understanding you can get this length. And VT you already know what is VT. So VT is threshold voltage. Get to source voltage. Okay, and one more point I would like to say here. So as in this case here we have seen, so as we are applying the VDS that is greater or larger value, there will be a depletion in the channel region is going to be taking place. So channel is going to deplete. So as the channel is going to deplete, we have seen in just now that this is the length of the channel. But now as the channel has depleted, because of the larger value of VDS value, there is reduction in this channel region is there. So this is now the reduced channel region. So now this is because of higher VDS value, the channel region is going to reduce. So in that case also the channel length also reduces. So instead of this is the initial length, now the new channel length is this only. So channel region length has reduced. So because of the application of higher gate to drain to source voltage, there is reduction in channel length. So this process is called channel length modulation. Channel length modulation. So channel length modulation takes place when VDS is greater than VD saturation. If we are increasing the VDS even greater than VD sat, then there will be channel length modulation taking place. Channel length modulation is basically going to reduce the effective channel length. So whatever effective channel length is there, that is initially L, now it is reduced to L dash, you can call it this L dash. So that's going to have a smaller channel length is now. So this is called channel length modulation. So this is similar to the modulation that taking place in JFET and also in BJTs. So base width modulation, okay, we have seen, and the channel length modulation we have seen in previously in the JFET also. Okay, so this is all about the operation of N-channel MOSFET. If you have any doubt, you can ask. Okay, so thank you. So we will see the next topic into the next class. Thank you.
Thank you, sir.
Thank you, sir.